Welcome back to ECE 442-542. Homework 2 is due in a couple of days on Friday. Exam number 1 is in a week. And you probably, if you're looking at the review material on D2L, you've probably seen the process for exam number 1, but I'll try to review that on Monday. We will have a review session on Monday, and I will try to record that. I think it will be recordable in that environment, but who knows? I never feel real comfortable with a new classroom, but the classroom that we will hold our review session on Monday night, the 9th of February, right after this class at 7 o'clock, will be in Education 353, which is on the 3rd floor, west side, north hallway in Education. If you go up to the Worlds of Words on the 4th floor, you've gone too far. We're below that 1 floor. If you need, well, hopefully you won't be there during lecture. I was going to say if you're there prior to the review session, but you should be here prior to the review session. But if you're not, we'll see you at the review session. And if you have questions or topics you think you would like to see addressed in that review session, there is a quiz. It's really just fill in the blank on D2L. You can type in your question that you would like covered, and I'll look at those prior to that review session. Today what I want to do is try to finish up material for exam number 1. We'll talk about properties of Z-transforms, and this can be used on homework number 2, some of these properties, and mainly the first one, which is really superposition holds, is one way of saying that. And then we will get into the frequency response for discrete time systems, and I will just illustrate that by a low-pass filter example. And we will try to dig up from your memory what you know about low-pass filtering in the analog domain or continuous time, and then we'll try to relate that to what we're seeing in the discrete time setting. And really we will be stepping forward in time. We'll be doing a discrete equivalent, which is something that will be in the future, but it's okay, we can mix and match. And so now, after today's class, the idea is you will be able to go home and program and do filtering in a digital system. That's the idea, based on this example today. Let's get started then with properties of the Z-transform, or you could say Z-transform theorems. That would be a valid way to refer to this. The first property is that of linearity, which really just says that if you have alpha 1 times some function in the time domain, f sub 1 of nt, plus a linear combination of another function, f sub 2, then if you actually know the Z-transform of f sub 1 and f sub 2, you can factor out that constant. That slides right out of this sum of the definition of a Z-transform, which allows you then to not worry about the scaling coefficients messing up what's happening. And now you can simply take the Z-transform of little f sub 1, weight that by the same scaling factor alpha 1, and add that to a scaled version of the Z-transform of little f sub 2, with the scaling on f sub 2 being the same capital F sub 2 as what it was on lowercase f sub 2. This will actually come into play, or can be used, on problem 5C, I believe, where you're asked to do the cosine of 2 angles. And I might just hint, you might review your law or your trig, cosine of A plus B. Maybe use the sum of angles formula to work that problem. That will allow you then to use the z transform of this cosine plus the z transform of a sine. And that should help you solve that homework problem. And that's using this property, this linearity property of the z transform. Another property which we've actually been using, we haven't really been talking about what we're getting in the time domain. We've been just multiplying signals and systems to generate an output. That's convolution or multiplication in the frequency domain is equivalent to this convolution in the time domain. Which means if you have two time sequences, f sub 1 and f sub 2, you can convolve those in the time domain with this convolution, which in discrete time is a summation. And if you take the z transform of that, that will be the equivalent to the z transform of little f sub 1, which gives you capital F sub 1 of z, times capital F sub 2 of z, which is the z transform of little f sub 2 of n. And that's what you should be familiar with from the analog case. It works in the discrete time setting as well. Convolution in the time domain is equivalent to multiplication in the frequency domain. And we will use that later if we have, and we've already been using really the right-hand side where f sub 1 of z might have been a system, f sub 2 of z might have been a signal. And now we're combining a system with a signal to generate an output signal, z transform. And that avoided us having to do this convolution of maybe the pulse response and this time domain sequence to get the output in the time domain. Another property that we have been using is the time shift property, which means that if we have the z transform of, let's say, f of n, and I will say plus or minus L, meaning I can either add L to n or subtract L from n, and now I simply have to match up the plus and minus over there on the z. I hope that's clear. And this is then f of z. Maybe what I should do is make one of these a little different color to maybe make it stand out. And in this case, n is the variable in the argument of f that is changing. That's the time index, and L is some fixed integer. Maybe that's 1, maybe that's 2, but you've been using that to go back and forth between the time domain and the frequency domain. When you have linear difference equations, you now convert that into the frequency domain by scaling or multiplying by z to the appropriate power of delays or advances in the time domain. Another property, I'm just running through these properties because I want to get to the frequency response, but the other property 4 is scaling. In the z-plane. Which means if you had some function of n in the time domain, and then you actually want to maybe hit that with, in this case, you could think of dividing by r and raising that r to the n so that at every n you're sort of dropping that. If r is bigger than 1, you're sort of scaling that f of n down. You're shrinking it down with each n. That's one way of sort of visualizing that. And if you wanted the z transform of that, you could actually obtain that. If you already had the z transform of little f of n, you could write down the z transform of r to the minus n f of n by simply scaling all the z's in capital F of z by changing the z's to rz. And you would have the z transform of this modified time domain waveform. And you might look at a very simple lowercase f of n. Look at a exponential. Little f of n is a to the n, for example. And now if you wanted the z transform of, maybe instead of talking about this, maybe I should sort of, suppose you had f of n equal to a to the n, where a is some constant. What is capital F of z? Do you remember that from last time? And this should be very quick by a week from today. Should be able to just do this very quickly. If I gave you this, you should say, oh, that was a gift, thank you, and just move right along. What is capital F of z if little f of n is a to the n? Did everybody hear that? It was very, what do I want to say? Shouted from the rooftop? Maybe not. Looked something like that, didn't it? Z over z minus a. And you could derive that if you wanted to. Now, maybe somebody says, oh, you know what? Actually, I want the z transform of g of n, where g of n is now f of n, let's say, what did I use, lowercase, r to the n, which is now r to the minus n, f of n. Then what is capital G of z according to this property? And you wouldn't even have to derive the z transform of little g of n from the time domain expression if you already know the z transform of little f of n. What does that property tell you to do? If you wanted partial credit, you would do this, right? But that's not quite there in terms of the answer, but now you simply, everywhere you had a z in the f of z, you can now replace that with rz over rz minus a. And you could rewrite that. You could factor out an r from both terms in the bottom and cancel the r's in numerator and denominator. Now you have the z transform of g of z. I'm sorry, little g of n. And you might just plug in some numbers just to see if this makes sense. Maybe you let a equal 1/2. What's that going to do in terms of a function of time? Can you see what that's doing? Little f of n, if capital A is 1/2, what do you have? You have an exponential, don't you? 1, 1/2, 1/4, just this exponential decay. Now let's say that r is 4. Now, if you look at little g of n, you can see that at each time step, you're dividing by 4 raised to a higher and higher power. So you would expect it to be collapsing much quicker. And that's actually what's happening over here with capital G of z. You know what f of z is. That's z over z minus 1/2. Now, g of z would be z over z minus 1/8, which is obviously collapsing much faster, and that's what this property would tell you is going to be true. You might just look at that on your own if you don't see it right now. One more property. Let's look at something that can save you time and maybe stress in terms of being able to find a final value without having to find the complete solution. Maybe you know the z transform of an expression. You can now use that to find the final value in the time domain. Suppose that you have the z transform of little f of n, and that gives you capital F of z. So let's say that that converges for z greater than 1. That means the region of convergence is outside the unit circle. And all poles of the product of z minus 1 f of z are inside the unit circle. Remember what you were doing with the final value theorem in the S domain. You were looking at S, f of S, where f is capital F of S. Here, S is similar to, or S equal to, at the origin is similar to Z at 1, so this S is getting replaced in a lot of these properties or theorems or relationships with this factor Z minus 1, where you would normally see S. So now we have Z minus 1 times F of Z. We want all of the poles of that expression to be inside the unit circle. Then we can apply this theorem, which says that the limit as n goes to infinity of the time sequence little f of n is going to be the limit as z goes to 1 of z minus 1 f of z. Just like s went to 0, now z goes to 1. And you're looking at this limit on the right, maybe saving you time in trying to figure out where is my time domain expression, little f of n, going as n marches off to infinity. Those are some properties that you need to tuck away and be able to use as needed throughout the semester, and some of them we're already using for exam 1 and homework 1, homework 2 material. Let's look at one more topic that hopefully I can get to the punchline. We're going to build up to this, but this concept I want you to be capable of using or performing what's needed on exam number 1. And that's this discrete time frequency response. And I'm going under the assumption that a lot of times when we learn new material, we learn it better if we can connect it to something we already know or that we are comfortable with. With that in mind, what I am wanting you to start thinking about is how And now think of a continuous time waveform. How will a sinusoid, think of some cosine waveform at a given frequency, how will that be filtered? Whoops, getting ahead of myself here. So how will a sinusoid be filtered by a low-pass filter? That you should already know about. That should be previous knowledge. And to illustrate that, what I want you to do right now is design a first order, and this is an analog, design a first order low-pass filter. An analog, and it can be passive. Design a first order low-pass filter. Go. This should only take you about 30 seconds. Because I haven't yet told you any kind of frequency. So you can make it right now a universal low-pass filter. And you could even draw a picture. Hint, hint. And if you've had me in a class, we better have covered this in an earlier class. At the junior level, like a 300 level class. Think of a circuit coaching you here. Time is about up. Do we need more time? What did we draw? I hope if somebody remembers a little bit about 320, maybe, you drew a RC filter. Here's the output, and there's the input. And now, what's the transfer function of that low-pass filter? Quiz 2. Pardon? Sort of. What is the transfer function of that RC filter? Now you can put it into the frequency domain if you're looking for partial credit. You could say, well, if he said transfer function, he must want it in the S domain, so I'll just capitalize things. What does R do when you transfer that from time domain to frequency domain? It turns into an R, doesn't it? It really changes a lot. It went into the phone booth and came out the same as it went in. Right? Didn't have to be a superhero. But what does change in this circuit? The capacitor, doesn't it? That's an energy storage device. It does contain an S variable. This is now 1 over SC, which allows us now, if you see it right away, that could be just a voltage divider to find V naught of S in terms of V sub I, or you could write KVL equations and then solve for V naught of S in terms of the current through that series branch. If you did a voltage divider, let me just say, or KVL, you could say that V sub 0 of S is now the impedance on the vertical branch divided by the total impedance And there is our transfer function of a low-pass filter. And maybe it's in an ugly form because you don't like that ratio of ratios in the numerator and denominator, but we can get a common denominator of SC in all the terms and just rewrite that as 1 over SRC plus 1. And if you wanted to, you could think of this as some time constant tau. Is that making you feel warm and fuzzy? This is a low-pass filter. It's an analog low-pass filter. You should feel fairly comfortable with that. We want to now translate this into a first-order difference equation so that we can implement it on our computer. We're going to find a discrete equivalent, but before we do that, let's make it a little bit more specific. Design this low-pass filter to have a bandwidth of 100 hertz. Go. Pick values for the resistor and the capacitor. Actually, just the product. Let's not even worry Josie. Don't wake her up. You don't need to go find a capacitor and a resistor. In reality, you would, but for now, let's just worry about the product of R and C. So now find the time constant tau, or the product RC that will give you, here's your task, 2 is create a low-pass filter with a bandwidth of 100 hertz. That's the 3 dB point, is 100 hertz. And you can talk it over with your friends if you decided to sit a little closer with somebody this lecture versus last time. How do you make this happen? I'm just going to take a nap up here in the corner. It's kind of dark. Is everybody finished? We have to make sure and keep track of our F's and W's, correct? we wanted a cutoff frequency of 100 hertz, and 1 over SRC plus 1 is not necessarily right in terms of hertz, is it? If you looked at the pole of that transfer function, that pole was going to have units of radians per second, right? That RC time constant is in seconds. S is radians per second. So we actually need omega sub c, which is 2 pi f sub c, 2 pi 100. Now we have 200 pi. And pi is, it doesn't matter that much for tonight. I know that'll make you nervous and anxious, but let's just approximate pi as 3 and just say that's 600 for omega c. That's what we want for a cutoff frequency or a break frequency, and that's going to be available to us from the denominator. Meaning we have this SRC plus 1, or this is now tau S plus 1 if we wanted to write it in terms of the time constant. We want to know what value of S causes that to vanish, and we want that value of S to actually be minus 600, don't we? Meaning this is going to say we have S is minus 1 over tau. That we need to be minus 600, or tau is 1 over 600. I'm doing this without a calculator, I apologize. I'm trying to think this through. So now I can divide 1 by 2, that's easy. Or I can divide 1 by 3, that's 0.333. The 1 by 6, that's a little different. So that's 0.333 divided by 2. I can do that. I can cut that in half. And now I have something like this. Or tau is 0.00167 seconds. Everybody get that for their low-pass filter, their capital H of S. You now can say that we have H of S that's this low-pass filter with a bandwidth of 100 hertz. And you could wake Josie up, get a C and an R, and build that, and now you can filter signals. And what do you know is going to happen with different sinusoids or cosines that are passed through that low-pass filter? You know which ones are passed and which ones are rejected with a cutoff frequency of 100 hertz. Now you could actually sing into that if you have a low enough voice and maybe hear it coming out, right? Because we can maybe make noises from 20 to 100 hertz. Maybe. Anything higher than 100 is starting to get attenuated, and actually right at 100, that's the 3 dB point, it's getting attenuated even at 100 hertz, isn't it? Well, how do we verify this? How do you justify to yourself that what you've now designed oh, and I think somebody told me don't write in red, but this isn't on your paper, right? So it's not screaming at you, it's not, I hope you're not getting stressed out by this red. I really did. I pushed the green, but it didn't switch over. So I'll finish this so you'll only be half stressed. Verification of the low-pass filter in the S domain. I promise we're going to relate this to a discrete time system, but this is now our transfer function. Can you sketch the Bode plot of that? You knew that was coming, didn't you? What's this doing at low frequencies, this transfer function? We have a DC gain of 1, don't we? And on a Bode plot, what does that mean? At low frequencies, we're going to be starting at 20 log of 1, which is 0 dB. We're going to be flat. If I just quickly sketch the magnitude until some frequency, and then we're only going to be sloping at one slope all the way till the end frequency, which is never going to be reached. What's this break point? And now let me say that this is omega. It's usually log of omega. We said this was 0 dB. This slope is minus 20 dB per decade, or a factor of 10. And that's 600. That's where we're breaking 600 radians per second. And what's the phase look like? Is it flat and then it kinks and that's it? The phase is more challenging or interesting, isn't it? It's now centered at 600, but now its interesting behavior is spread across 2 decades. This is now the phase. This was the magnitude. Whoops, I was calling it H, I think, wasn't I? We start at 0. Where do we end up in our phase? The only frequency term we have in this transfer function is in the basement downstairs. That's the pole factor. And we only have 1, so it's going to give us 90 degrees. And since it's downstairs, it's minus 90. We're going to go from 0 to minus 90. We'll make that transition over these over this 2-decade interval, straddling the break frequency of 600. So if I injected, this is now the picture that we have. And if I said, let's assume the input is now 2 cosine of 500t. Now can you tell me what's going to happen to that v sub 0 of t in the steady state? If you sketch this Bode plot, you now know, oh, there's 500, and 500 is right here. This at 600 is minus 45 degrees. And in our straight line plot, we would know that the magnitude hasn't decreased at 500. In reality, it is rolling off because it's going to be down minus 3 dB right at 600 in reality. Meaning this guy is going to be 2 times the magnitude of h of j 500 cosine 500t plus the phase of h of j 500. That's the sinusoidal steady-state output response due to a cosine or a sinusoidal input applied to a linear system. You simply evaluate the transfer function at J500, which is right on the imaginary axis. And we could do this graphically. Now we actually want the pole zero form of this, which says there's our pole zero diagram of this filter. To evaluate this magnitude, we could find L sub p, and we could find this phase theta sub p graphically from this S-plane, just walking up the imaginary axis and looking at this length at J500 and this angle theta sub p. Meaning, if we now have h of J500, we have 600 over J500 plus 600 as a complex number. We're just replacing S with J500, and that denominator is a complex number that has a length and an angle. And that length and angle are these L sub p's and theta sub p's. This is now 600 over L sub p at an angle of theta sub p, where L sub p is 600 plus J 500, and the angle is this inverse tangent of 500 over 600. I hope this is seeming somewhat familiar. If we computed this, we would end up with 0.768 at an angle of minus 39.8 degrees, which now allows us to write down V sub 0 steady state of t as 2 times 0.768, which is a little bit more than 1.5, cosine of 500t minus 39.8 degrees. Does that seem reasonable for our first order low-pass filter when we inject into that first order low-pass filter a cosine of frequency 500 radians per second with an amplitude of 2? Says we have some delay, that's the minus 39.8 degrees. Obviously, you would need to convert that to radians if you're trying to evaluate that cosine. And you could then find the value of the output at any time t from this formula. We now want to find a linear difference equation. so that you can now program that into your computer or microcontroller. You want to now build a low-pass filter in a computer, first order, with these same or similar properties. So how do we do that? We have the transfer function. We have this ratio of output voltage to input voltage is 1 over tau s plus 1. We can cross multiply and have tau s plus 1 times v sub 0 of s equaling v sub I of s. Can you now give me a differential relationship between the input voltage and the output voltage in the time domain from that expression? What's multiplication by s in the frequency domain? That's differentiation in the time domain, meaning we can now write this as tau v naught prime of t plus v naught of t equaling v sub I of t. And there is our first order differential equation that is, because we know what tau is, that's that 0.00167. This is now a low-pass filter with a bandwidth, or it solves the dynamic relationship between the input and an output of a low-pass filter in the time domain. We will develop better tools for finding discrete equivalence than what we're doing now, but let's just approximate this derivative let me say approximately dV naught, that's just a difference between the voltage at two different points in time, and dt is just a delta t. Let's say that this we will write as v naught of n plus 1 t minus v naught of nt all over n plus 1 t minus nt. Do you see what we're doing there to approximate that time derivative? We're just looking at the delta v over delta t. And the denominator simplifies quite nicely. We have nt plus t minus nt. The nt's go away and we just have the sample period capital T in the basement. Upstairs we have to keep track of those two different values of the output, one at time step nt, the other one time step ahead of that, n plus 1t. That's all we're doing. We now have this way of approximating a derivative by letting that be v naught of n plus 1 capital T minus v naught of t all over t. What is still unknown in this derivative approximation? We haven't yet selected the sample period, have we? Capital T. But do we have a feel for what we might compare that with? this is approximating, we're trying to approximate this low-pass filter with a bandwidth of 100 hertz. So we have a bandwidth. How fast do we sample in terms of bandwidths? Well, he's been telling us 30. Let's just tell him 30. What's that mean? So now let's just make our sample period 30 times, or based on a 30 times difference between the cutoff frequency of our low-pass filter and the sampling frequency. What's our cutoff frequency in radians? So now we're asking, what is capital T, where T is our sample period, in this difference equation that we're trying to build up, and we already know our cutoff frequency is 600 radians per second, which means in terms of radians per second, our sampling frequency, we want to be 30 times omega c. Omega sub s is now 18,000 radians per second. And we can relate that omega sub s to our sample period. Our sample period now, just solving for that, is capital T is 2 pi over omega sub s. And you know what I'm going to do next. I'm going to approximate pi with 3, and omega sub s was, what was it, 2 times 3 times 1,000? No. Wasn't 6, was it? It was 18. So let me say 3 times 6 times 1,000. Those 3's cancel, and now I have 1/3. Or I have a sample period, capital T, of 0.000333. And now what I want to do is use that to come up with a difference equation from our differential equation. Question? Pardon? So 30, we're going to learn what the significance of 30 is later. Right now I'm just saying it's a rule of thumb, but it's a nice trade-off between sampling a lot faster than the Nyquist rate and not so fast that, I mean, you could say, oh, just make that 1,000,000 times omega c, but then you're losing resolution. Now you're maybe jumping up 10 to the minus 7 in between samples, and that's not giving you any useful information. So it's this numerical precision and resolution that's a trade-off with this 30. Right now, just sort of accept it and say, okay, it's 30 times the bandwidth is what we're using for a controls setting. So that is, if we use that, and you could use something else. If you said, I can't sample that quickly, then you might say, okay, let me see what happens if I sample it 10 times the bandwidth, and then look and see if that's going to give you acceptable behavior in your particular system. Right now, that's just something that we're starting with, and we will just use for now. What we want to do now is we want to convert that first order differential equation into a first order difference equation. And our differential equation was this tau v naught prime of t plus v naught of t equaling v sub I of t. And to push that into a difference equation, we were simply replacing the derivative with this finite difference. The finite difference being v sub 0 of n plus 1, capital T, minus v sub 0 of nt all over t, plus v sub 0 of nt equal v sub I of nt. Let me clean up that tau over t by multiplying through the inverse of that. And I can now say that I have v naught of n plus 1 t minus v naught of nt is equal to, oh, let me not do that yet. Let me keep the v naught over here, plus capital T over tau v naught of nt equaling capital T over tau v sub I of nt. If I solve that for the next sample of the output, then I have 1 minus capital T over tau v naught of nt plus capital T over tau v sub I of nt. If you crunch the numbers, 1 minus t over tau is 1 minus 0.19994. That's roughly 0.8. So let's just call this coefficient that scales v naught of nt 0.8, and this, let's just round the 0.1999 to 0.2. And now we have our difference equation. We have v naught of n plus 1 t equaling 0.8 v naught of nt plus 0.2 v sub I of nt. This is now a first-order difference equation that produces a low-pass filter with a bandwidth of approximately 100 hertz. I say approximately because I've been changing pi to 3, etc. But it's close. And now do you see how you could actually implement this? Somebody could give you a cosine waveform. You would just need to sample that at capital T, which is 0.000333 every 0.00333 seconds. You would sample that cosine. That would be your f sub I of nt. Maybe you say, let me start this at v sub naught at 0, and then you number crunch this. Every time step, you get a new v naught of n plus 1 t. And you can now filter that input waveform if somebody gave it to you. And if it was noisy, if it had noise that was at 500 hertz, it should be getting filtered or removed from this difference equation. Do you see this is just an algebraic relationship now? You've converted Josie's RC filter to a first order difference equation that you can simply punch numbers out. And you could program this into a computer. You could write a program that would implement this difference equation. Now, and you could put this in an Excel spreadsheet if you wanted to, and have a low-pass filter in an Excel spreadsheet. What if we inject into that now a similar sine wave or cosine wave that we had before? What if v sub I of nt is equal to 2 cosine 500? Now what do we do? We want it to be similar to what we were doing in the continuous time case, and that was 500t. What are we doing with t? We're just sampling it, aren't we? So now we're replacing this little t, which is a continuous variable, with a sampled set of points on the time axis. T, capital T, we've already picked. That's that point 0.000333. If we multiply that out, we have cosine of 500 times t, which is 0.1, whoops, 0.1665 n. What if we use that as v sub I of t, where I've used this argument in the cosine? That's really this theta sub d was 500t, where this is the omega sub d, the damped frequency, and this is our sample period, capital T. Can we find v sub 0 of SS? You could recursively produce this, couldn't you? You have the linear difference equation. What we want to do now is think about a closed form expression for v sub 0 of SS. And how did we do it in the analog case? We simply evaluated our transfer function along the imaginary axis. That was in the S-plane. What's the imaginary axis look like in the Z-plane? The unit circle. Now we need to figure out, how do we find something like this h of j500 for our discrete time system if we're trying to find v naught of SS? It's the same process that we followed. It's a similar process. What is h of z? We know what the difference equation is. Can you z transform that? What happens when we z transform a function of time at time n plus 1 sample periods? This gives us our multiplication by z, doesn't it, in the frequency domain. This is an advance, so this is z, v sub 0 of z. And now little v naught just becomes big capital V naught scaled by 0.8. Likewise with v sub I. We group similar terms, and now we have v naught is 0.2 over z minus 0.8. This is what we wanted for starters. This is now h of z. How many poles do we have? One. Does that seem reasonable for a first order difference equation? Yeah, in an S domain we had one pole for a first order difference equation. Where is our pole? Now I'm going to get in trouble because I probably won't be able to sketch this very well. Ooh. Oh well, use your drawing skills better than I can and create a unit circle that doesn't have a dimple in the bottom. But that's supposed to be a nice circle. Ooh. That looks even worse away from my tablet. I apologize. But where is the pole of our low-pass filter? It's at 0.8, isn't it? Uh-oh, it's in the right half plane. Does that matter? Yes or no? No, it's inside the unit circle. That's what matters, right? It's a stable filter, which is good. Now what we want is we want to find the point on the unit circle that corresponds to this sinusoid, 2 cosine of 0.1665n. Now if we just looked at the cosine part, don't worry about the 2, the angle theta sub d is 0.1665. That's in radians. That tells us how far or what size of an angle we have. Now we're looking at some point right there, where this is now unity. That's the cosine, and we want to know where are we on that circle. I'm going to suppress the capital T, but this was 2 cosine of 0.1665n. This is our theta sub d, which was our omega sub dt. This is in radians. What kind of an angle do we have in degrees? If we convert it by 180 over pi, we end up with this being 9.54 degrees, if you can think easier in degrees than radians. This dot that I sketched, it's not very accurate. That needs to be roughly at 10 degrees. Then what do we do? Well, now we simply need to evaluate our transfer function h of z on the unit circle, and we know now where to be on the unit circle, e to the j theta sub d. or this is at 1 at an angle of 0.1665 radians, or 1 at an angle of 9.54 degrees. Which really means that we are moving to that point and that angle, and that's what's going to be injected into or result from this h of z evaluated at that point on the unit circle. H of z was 0.2, e to the j 0.1665 minus 0.8. That's what we're doing by simply replacing z with e to the j. Now let's just go back to Euler to simplify that complex exponential. E to the jx is cosine x plus j sine x. We now have cosine of 0.1665 plus j sine cosine of 9 degrees is 0.9862. Sine of a small angle is approximately that angle, and that's what we're seeing. If we keep doing the complex algebra in the basement, we have 0.18617 plus j 0.1657. And if you look at what that means that to go from point 8 to that dot, we have to move over horizontally, 0.18 whatever it was, and up j 0.165 to get there. And we can then find its length and angle dividing that out, we end up with 0.8 at an angle of minus 41.676, and that can now be substituted in to our time domain output sinusoidal steady state response. This is 2 times the gain at that frequency, cosine 0.1665 minus 41.676 degrees, or this is now 1.6 cosine and that should look somewhat consistent with what we had in the continuous time case. Did we have 1.5 something cosine of 500 little t minus 40 degrees? I think was something like what we had for v of t. Now we have derived this frequency response, which is really just going back to this curve. We know where our poles and zeros are. We just had the one pole at 0.8. We knew where we were on the unit circle, and we could measure that distance if we had accurate enough ruler, and we could measure that angle, and that would be how we would adjust the magnitude and change the argument of our cosine to generate this sinusoidal steady state output. But now you know how to design filters for a discrete time system. If you want to, you could make it a 5th order, Butterworth, and build out your difference equation using the same kind of strategy that we've done here. So now we finished a few lectures in this class, but now you can do all sorts of filtering if you want. Yes? Well, you should want. Now you don't have to bother Josie for parts. You can just put it onto your computer. I'll see you on Monday.